Hi, everyone. I'm really happy to speak about our recent work today. So our work is called Why Diffusion Models Don't Memorize, the Role of Implicit Dynamical Regularization in Training. So I'm Raphaël Urfin. I'm a PhD student at ENS, and I did this work in collaboration with Tony Bonner, a former postdoc at ENS and now has a permanent position in Paris-Saclay. And we work with my PhD supervisors, Giulio Biroli from ENS Paris and Marc Mézard from Bocconi University. And so we are really happy to have received the Best Paper Award at NeurIPS San Diego. Okay, so today I'm going to discuss about diffusion models. So most of you know a lot about diffusion models. So there are a class of generative models that have achieved state-of-the-art performances in a variety of tasks. So now you can generate high-quality images with simply a prompt that you put into your favorite LLM. You can generate high-quality videos that are really hyper realistic, like this one. So it has a lot of also implications for society. And also it has a lot of applications in many fields of science. So maybe one field that is really promising is a weather forecast, where methods based on different models, they manage to have to compete with traditional methods that were used with PDs. Okay. So we all agree that different models have a lot of applications, and I would like to briefly summarize what are the principles behind different models. So say you want to generate images of dogs. So you have a data set of images of dogs like this one. And the first step is called the forward process. So you will gradually noise your data sets with your favorite noising scheme. So for instance, you can take the Orstein-Leveck scheme, and this will transport your data distribution into Gaussian white noise. Okay. Then there is a second process that we call the backward process. So you start from Gaussian white noise, and your goal is to have a process that will denoise this Gaussian sample into a new sample from your target distribution. So here, an image of a new dog. And this can be done if you know the score function S. So if you do a diffusion in reverse time in this force field, so the score function, then you will be able to generate new samples from your target distribution. Okay. So here, really, the key to generate new samples is the score function. So you have a lot of different formalisms. So you have the variance exploding scheme, variance preserving scheme. Some people use flow matching, which is deterministic, stochastic interpolance. And basically, everything I'm going to say today is also applicable to all those related formalisms. But I will stick to the one I presented just now. Okay. So for my noising process, the score function I want to learn is really simple. It is the gradient of the log probability, PT, where PT is the marginal distribution of your noisy samples. Okay. So if you know PT, it's really easy to estimate the score function. You compute the gradient of the log. But in practice, PT is unknown, because what is the distribution of the images of dogs, okay? And so what really saves us is through this formula. So this formula tells you that the estimation of the score function can be recast as an optimization problem, okay? So the score function is the minimum of this specific loss that is called the denoising score matching loss. So basically, if you have an optimal denoiser for your target distribution, then you can use the usual. You can use it to estimate the score. And to optimize this loss function, you can use the usual toolkit of machine learning. So you take a neural network and you apply your favorite optimization scheme, such as ADAM, SGD, on this specific loss. And at the end, you will have a good estimation of the score function. Okay, so diffusion seems to be really easy because once you have access to this estimation of the score function, you can generate your samples. And so what the theory of deep learning tells you, it's so something called benign overfitting. It tells you that if you have a really large model, then you will, okay, overfit on your specific data sets, but you will have good performances on the test sets, okay? So this concept of deep learning tells you, okay, you don't need to think about your model. You take a really big, deep neural network, you train it, and it will have good performances on your test loss, okay, even though it overfits on your data sets. But the picture is really different for diffusion because for diffusion models, if you estimate the loss on finite data sets, so you look at the empirical loss, then the minimizer of your empirical loss is going to be the empirical score function, okay? So it is going to be this function, and the empirical score, it only memorizes the data sets, okay? So at the beginning, the empirical function looks like the target score function, but at the really end of the generative process, here we can see all the trajectories will collapse onto training points, okay? So this empirical score will lead to memorization, and the only way to prevent it is to have a really large data sets. So you need your data set to scale exponentially with the dimension of your data. So this is the dimension of the data. So this is a manifestation of the curse of dimensionality that is present everywhere in machine learning. And so it tells you that there is no benign overfitting in diffusion models. So you need to be a bit smart. If you take an overparameterized model and you train it on the empirical loss, then you will just memorize your data sets, and it's not the regime you want to be in. Okay, so this was the theory, but what is happening in realistic settings? So, okay, you have partial memorization. So if you give a specific prompt to an industrial diffusion model, so like a daily stable diffusion, if you give it a specific prompt, sometimes you can get an image that already exists on the internet. So you have this famous example. And of course, this can lead to copyright issues, privacy issues. So this is really something you want to prevent. So you want to prevent this partial memorization. Okay. And then there is also really motivating empirical work that was done by Zarakat Kodai, Stefan Mala, and co-workers. So what they did is that they took two distinct data sets of images of faces, so S1 and S2, and then they trained two different neural networks to learn the score for the different data sets. And then they looked at what was the two different models generating. So if you have two data sets of size 1, then your neural network will only memorize the training points and generate exactly the points that were in the training sets. But when you increase the size of the data sets, you see that at some points, so for n equals 10 to the 5 images in your data sets, the two models, they converge. Okay, so they will generate new images of faces that are the same and that are independent of the training set you use to train your diffusion models. So they really generalize. So it means that they have learned the true distribution of images of faces. And what is even more striking is that this happened for a dataset size n. So dataset n star here, 10 to the 5, that is way smaller than the prediction I had told you before. So I told you that n needed to scale exponentially with the dimension. And here we see that empirically, it's something that is small and that can be achieved in practice with a reasonable dataset size. Okay. So there is a conundrum between theory that tells you that different models will always memorize and what is happening in realistic settings, where you see that you can generalize with data set of size that is achievable in practice. Okay. And so there has been a lot of different works that have tried to understand how memorization is prevented in different models. Some people studied, for instance, the data structure. So images, they lie on a manifold that is of intrinsic dimension that is way lower than the ambient dimension. And so this will lower the theoretical threshold I discussed before. Some people try to discuss about the stochasticity of the process and of the loss. So because there is noise everywhere, maybe it helps generalization. Closer to our work, there are people looking at architectural biases. So they claim that if I try to learn the score with a neural network, it has biases, symmetries, a finite expressiveness, and therefore it cannot learn the empirical score, but it will learn an approximation that is going to be smoother and that will allow generalization. And finally, so our work tries to fit in this line of works. So we try to explain this by dynamical regularization of the training dynamics of the score. Okay, so here I'm going to summarize a bit our results. So I'm plotting a phase diagram. The x-axis is the number of parameters of my model, so the neural network that tries to model the score. And the y-axis is the number of data points I use to train my neural network. So there's the first regime, so the large dataset size regime, large N regime, where I have architectural regularization. So it's the regime that was discussed by so the paper by Zara Katkodai. So they claim, okay, my neural network has a finite expressiveness, and I have enough data points to learn the true score. So in this region, I won't learn the empirical score, but I will learn actually the true score that will be able to generalize. Then I have this second regime, so the low number of data points regime, where I will always memorize. So if I have only one data point in my training set, I will only memorize it and I won't be able to generalize. Okay. And then there is this third regime that we investigate that we call dynamical regularization. So in this regime, my model is overparameterized. I have a lot of parameters, so I can express the empirical score. Okay, but thanks to implicit dynamical regularization of the training dynamics, I will be able to generalize and learn a score that is going to generate new samples. Okay. And so in this region, what is really important is that the emergence of a separation of timescales. So here I'm presenting in this figure two quantities of my model as a function of the training time tau. So in blue, I'm plotting the inverse quality of the images I'm generating. So say the FID for images. And then in red, I'm plotting the fraction of memorized data points. Okay. So first, when I start to train my model, I see that the FID decreases. So it means that I'm starting to generate high quality images. And this will happen over a time scale that we call tau gen. Okay, so the generalization time scale. And then there is a second time scale, tau mem, where I will start to see that I'm starting to memorize data points. Okay, so I see that the fraction of memorized data points start to increase. And what is really crucial here is that these two timescales are well separated. And the empirical and theoretical prediction we have is that the ratio of the two scales linearly with the dataset size n. Okay, so if I have a large enough data set, those two timescales are going to be well separated, and I will be able to do early stopping of the training dynamics. Okay, so if I early stop my training after tau gen and before tau mem, then I will be able to generate high quality samples without any memorization, which is exactly the regime I want to be in for generative AI. Okay, so to support this claim and this phenomenology, we first did some numerical experiments. So we looked at a data set of faces, so celeba, images of celebrities, We took a state-of-the-art architecture, so UNets for our neural network, and we trained our neural network with gradient descent on the denoising score matching loss. And so our results, so here I'm plotting the same plot as before. So I'm plotting the FID, and so the full line is the FID, and the dotted line is the fraction of memorized data points as a function of the training time, so the number of epochs tau. Okay, and the different colors are for different dataset sizes. Okay, so I do see that on the first timescale togen that is independent of the dataset size, I'll start to have images of high quality, so my FID decreases. And only later, I see that the fraction of memorized data points start to increase. And you see that for a large dataset, the two timescales are separated, and that the timescale for memorization increases when I increase the size of my datasets. Okay, while the timescale for generalization, it's independent of the dataset size. And on the insets, I'm plotting so the fraction of memorized data points as a function of a rescaled training time, so tau over n, the dataset size. And I see that all the curves collapse, indicating that this is indeed the timescale for memorization, so that it scales linearly with n. And so for those who are interested on the way we compute the fraction of memorized data points, so what we do is that for every training time tau, we generate a lot of samples from our model. And then we look at the two closest data points, NU1 and NU2, in our data sets. So the closest in L2 norm. And we have this really simple and naive condition to say whether we have memorized or not. So we look at the ratio of the L2 norms. And if it's below a given threshold, then we say that the sample was memorized. So, okay, it's a really naive criterion, but it's used in a lot of papers in the literature. So we took this one. Okay, and so here are some images we generated. So if I early stop at 10 to the 5 epochs, I see, so here the left column is the images I've generated, and the right column is the nearest neighbor in the datasets. So I see that the images are the same quality, and they are different. So I have not memorized yet. While if I early stop later, so the red dotted line, red vertical dotted line, I see that all the points I generate, they collapse onto training points. So you see that the images on the left and right columns, they are the same. So I've really fully collapsed on my data sets. And so I can do more or less the same phase diagram I've presented you before. So I can take several models with a different number of parameters p, different dataset sizes, and I can look when I'm starting to memorize where I don't see any memorization, and I can have this kind of a phase diagram where I can see all the regions I explained before, and how let's say the transition between generalization and memorization changes depending on the early stopping. So depending on when I stop the training, so the earlier I stop it, the better it is for generalization. Okay. So this was our experimental results. And so we wanted to have a really simple analytically tractable model that exhibits a separation of timescales. Okay. So to do this, we studied the random features in neural network. So it's a really simple toy model that has been studied a lot in the machine learning theory literature. So it's 2 layers neural network. Okay, so it takes inputs in dimension d, or data points. Then there is a first layer W that takes them into a feature space of dimension p. And then the last layer A brings them back in dimension d. So it's like the score function that is a force field from RD to RD. Okay, And to simplify our analysis, we take the weights of the first layer randomly, and we fix them during training. So the W's are frozen, and the only weights that are learned are the A's, so the second layer. Okay. And so, okay, I have sigma, which is my activation function, W, the first layer that is frozen, and A, the last layer that I'm learning. So the motivation for studying this really simple model is that it captures a lot of behaviors from deep neural networks. So in the early 2020s, it was studied to understand the double descent phenomenon. So the benign overfitting that happens in supervised learning. And so this model has had a lot of success before for supervised learning. And so, okay, we wanted to see if the phenomenology I described before was also happening for this really simple, shallow neural network. And so for analysis, so we train this model on the dataset of n data points from a given distribution that needs only to be well behaved regarding its tails. We look at the high dimensional regime. So it's the classical regime people look when studying this model, and it is the regime in which we are for deep learning. So I have a lot of data points, a lot of parameters p, and I am in high dimensions. And to simplify the analysis, we fix the diffusion time t, and I look at the gradient flow dynamics on my empirical score matching loss. Okay, so this loss, and okay, I do a gradient flow on it. And so this is a really simple analytical problem because thanks to all my simplifications, this is a convex problem, and I can study the timescales of the training dynamics easily by looking at the Hessian of the problem. So the Hessian is this matrix U, which is a random matrix. And if I know the eigenvalues of this matrix, it will give me the timescales of my training dynamics. So the timescales are the inverse eigenvalues of this random matrix. Okay, and so there are a lot of tools from random matrix theory one can use to study this matrix, such as the Gaussian equivalence principle. And so when you study this matrix, you realize that the spectrum is quite interesting. So here, and so the inset inside the plots is a zoom near zero. Okay, so I have two parts in my box, the orange one and the blue one. And what I see is that I have two well-separated bulks in the eigenvalue distribution. So the orange one and the blue one. So as you can see, I need to zoom near zero to see the blue bulk. So it shows that the two parts are really well separated with respect of the eigenvalues. And this will give me well-separated timescales. Okay, and so the histograms is the empirical eigenvalue distribution, and the full line is our analytical prediction. So okay, it fits well for the empirical eigenvalue distribution, and so you can even tune the rho sigma, so the covariance of the data sets, and our results still hold. And so the theorem we have for our model is that in the overparameterized regime, so I have a lot of hidden neurons P. So it's larger than the number of data points n, which is itself larger than the dimension. The spectral density rho of my Hessian U has 3 parts. So the delta peak in blue at 0, that is irrelevant for our problem. Then I have the first bulk rho 1 that is in blue. And this bulk has really small eigenvalues. So the scaling is 1 over n, where n is the dataset size. And this will give me the timescale of linear width n that I have found in the experiments. So a timescale that memorization timescale that scales with n. And then I have in orange another bulk that will coincide with the population Hessian. So this bulk is not due to it's not it's going to be the same if I have an infinite data set. Okay, so if I take the expectation over my data set, I get the same bulk. So this is really linked to generalization, and this will give me the timescales of other one that are independent of the dataset size, and this will allow me to have generalization. Okay, and so here are the curves, the empirical curves I obtained for my really simple analytical model. So I'm plotting on the left plot the train and test losses. So the train loss is in full line and the train loss is in full line and the test one is in dotted line for different data set sizes. So psi n is the rescaled data set size. So I see that in this model, I have this phenomenology. The larger the dataset size is, the later I will see the increase in the test loss. And when I rescale everything by my prediction for term m, in the inset, I see that all the curves collapse, indicating that it's indeed the right timescale for overfitting. And on the right plot, I'm plotting the error on the true score. So S star of t is the true score of my distribution. And I see, so at the beginning of the training, the error on the score, it's decreasing. And then later, way later on the time scale that increased with n, I will see that I will go away from the true score because I'm now learning the empirical score and memorizing. Okay, so this simple model captures the phenomenology of the experiments I showed you before, and we can so do math on this model to have the right predictions. Okay, so thank you very much for your attention. So to conclude this presentation, we have shown that diffusion models have several phases regarding their learning, depending on the size of the data sets and the number of parameters. What we show is that there is a phase that we call dynamical regularization, where even though your model is overparameterized, you can still generalize and prevent memorization if you do early stopping of the training dynamic before the memorization regime. So I thank you for your attention, and I am happy to answer all of your questions.